Hey, what's up, guys? Um, Today we're going to be kind of going into our next topic here, and it's all going to be about exponential growth and decay. So, when we're talking about exponential growth and decay, we're using the exponential law and the law of uninhibited growth or decay. Right? And what that means is we're talking about populations, right? And that could be people, it could be bacteria, it could be any number of things, right? But when we talk about it, we're going to be using this equation here, right? This A equals P times E raised to the RT, right? And what that is P is the original amount of a quantity or population, right? And A is the amount after the amount of time T increases, right? So R in this case is the rate. And when R is greater than 0, it means that the amount is increasing over time. And when R is less than 0, it's going to be decreasing over time, right? And a big vocabulary that we're going to see every now and then, and we'll go over some examples of this too, is half-life, right? And half-life is the amount of time it takes for a quantity to decay to half its original amount. All right, so let's go ahead and let's look at an example here. All right, so example number 1. The number of bacteria present in a culture at time t in hours grows according to the function A equals 1000 e to the 0.01 t, right? So it's using the equation here, and it's just giving us the value for p, right? In this case, p would be 1000, and it's giving us the rate, the r, right? R is 0.01, right? A is asking, determine the number of bacteria at t equals z hours. So what it's saying is, if we plugged in 0 for t, what would the amount be? All right, so we would have A equals 1000 times E raised to the 0.01 times 0. Right? And we know anything times 0 is just 0, so this would really be E raised to the 0. Right? And knowing our exponents, anything raised to the 0 power just turns into 1. All right, so this becomes 1000 times 1. So it's just 1000, which makes sense, right? No time went by, so the amount wouldn't change. It would just stay the same. It's 1000. Right? What is the growth rate of the bacteria? Well, that's given in this equation right here, right? It's 0.01. And what that means, right, 0.01, it's asking it kind of as a percentage. We could rewrite it as 1%. Right? So it's growing at 1%. 1% every hour, I should say. All right, what is the population after 4 hours? Okay, well, it's asking what is the amount, right, after 4 hours. That would mean if t equals 4. So we plug in our equation, we have 1000 e to the 0.01 times 4 this time, right? So what we can do is 0.01 times 4 is just 0.04, right? And we can just plug this into our calculator, make it nice and easy on ourselves, right? We would just do e raised to the 0.04 power times 1000, and we end up getting 1040.8. Right? If we wanted to, we could even round that up, right? Because when we're talking about bacteria or even the population, let's say if it was the population of people in a certain area or whatever, right? You can't really have a fraction of a person, right? So we'd always want to round. So it's 1040.8. We would round that to 1041, right? Because we can't really have a fraction of a bacteria. So D is asking, when will the number of bacteria reach 1,700? All right. So what this is asking is, okay, now we know the amount. We want to know the time. All right. So we would plug in the amount, 1,700, and that's going to be equal to 1,000 times e to the 0.01 t. All right. We can divide this 1,000 over. Right, we can do 1,700 divided by 1,000, and we end up getting 1.7 is equal to e to the 0.01 t. Right, and from here we have an exponential equation where the variable is the exponent, right? So we know we're going to have to transform it into our log function, right? And we can do that by saying, and I'm going to write it over here, log base e of 1.7 is equal to our exponent, which was 0.01 t. Right, and log base e, well, that's just the same thing as the natural log, right? So we can rewrite this as ln of 1.7 is equal to 0.01 t. Right, we can divide this 0.01 over, and we can say, well, t is going to be equal to the natural log of 1.7 divided by 0.01. Right, and if we plug that into our calculator, remember we just hit the natural log of 1.7 divided by 0.01, we get about 69.31 hours. Right, and you kind of just round it out there. Right? So that would be how we would solve for the time in a problem like this, right? Now, letter E is asking, when will the number of bacteria double? Right? So to know when it's going to double, we have to know how much it's starting with, right? And it gives us that in this original equation, right? It's starting with 1,000, right? That's the current population, the original population, 1,000. So we want to know, when is it going to be? 2,000. All right, we set that equal to 1,000 times e raised to the 0.01 t. All right, we can divide this 1,000 over again. All right, so 2,000 divided by 1,000, well, that's just 2. So 2 is equal to e to the 0.01 t. Right, and again, we just have to convert this to that log form, right? Which we already know it's going to be the natural log, because it's going to be log base e of 2 is equal to our exponent here. We can say 0.01 t. And solving for t, we get t is equal to the natural log of 2 divided by 0.01. Again, we get t is just about 69.31. And I'm really sorry, guys. I accidentally wrote down the answer to this one as this. This shouldn't be 69.31. We can cross that out. So if you were following along, we would know the answer is actually 53.06. And that's why you should always double check your work, right? So sorry, again, I just accidentally wrote this answer up here, right? But this is the correct answer to letter D, and this is the correct answer to letter E, right? So moving on to number 2. It says iodine 131 is a radioactive material that decays according to the function A equals P times E raised to the negative 0.087 T, where P is the initial amount present and A is the amount after T days. What's asking, what is the half-life of iodine 131? Right? And going back to the beginning, remember half-life is the amount of time it takes for a quantity to decay to half of its original amount. So what it's saying is that the amount has to be equal to 1/2 of the original, right? Because that's the half-life. It's saying how long is it going to take for the amount to be half of what it was. All right, so we can just kind of use that and plug in 1/2 p where we have a here. Right, so we can rewrite it like this. 1/2 p is equal to p times e to the negative 0.087 t. Right, and these p's, they're going to cancel out, right? We can divide that out, and we end up getting 1/2 equals e to the negative 0.087 t. Right, and then again, we just like we've been doing, right? We're going to convert it to that natural log, right? So it's going to be natural log of 1/2 is equal to our exponent here, negative 0.087 t. Right, and again, we can solve for t. It's going to be the natural log of 1/2 all over negative 0.087, which is just about 7.97 days, right? And it's important to keep track of the units here, right? It's given that the time is in days, right? And the problems before, it was given it's in hours. All right, so just something to be aware of. Right, the units can change sometimes. So let's keep going. Number 3. Right, a culture of bacteria obeys the law of uninhibited growth. Okay. A is asking if 500 bacteria are present initially and there are 800 after 1 hour, how many will be present in the after 5 hours? Right. So this one it's missing a piece of information, right? We need to know the rate, but luckily it gives us the present and the after and the time. Right, so we can use that to solve for the rate, and then we can figure out how many will be there after 5 hours. Right, so it's saying we can go, the after amount is 800, and that'll be equal to the present amount, which is 500, times e to the r, because we don't know what it is, times the time, which is 1. Right, so we can divide this 500 over, and we get 1.6 is equal to e to the r, because r times 1, it's just r. Right? We can convert that to our natural log form. So this is natural log of 1.6 equals r. Right? And we can leave it like this, right? Because if we solve for the natural log of 1.6, we end up getting a really long decimal. So it might be easier just to leave it as natural log of 1.6 for now, because we're going to have to plug it into the equation again, right? Because now we have to solve what's the after amount, where the present amount is still 500, and the rate this time we know is natural log of 1.6, and that's going to be multiplied by the time, which is now 5 hours. Right, so for this one, we can just plug it into our calculator. Right, we can do 500 times e raised to the natural log of 1.6 times 5. And we end up getting, it's roughly 5,242.88. But again, right, we're dealing with bacteria. We can't really have a fraction when we're dealing with population. So we would round that again to 5,243. And again, we just left the rate as the natural log of 1.6 just because it'd be a little bit easier to keep track of, right? So moving on to B, how long is it until there are 20,000 bacteria? Okay, so this time it's giving us the amount. It's 20,000, All right, we know the original is still the same. It's 500, right? And that's going to be times e raised to our rate, which we figured out is that natural log of 1.6. And we're solving for time. All right, so we can divide this 500 over, and we end up getting 40 is equal to e times the natural log of 1.6 times t. Right, and here, same thing as we did right here, right? We would change it to that natural log form. So we can say natural log of 40 is equal to our exponent here, which is natural log of 1.6 times t. Right, in solving for t, we can divide this natural log of 1.6 over, and we get t is equal to the natural log of 40 divided by the natural log of 1.6. All right, and when we plug that into our calculator, we end up getting that t is just about 7.85 hours. All right, so those are some really good examples of what uninhibited growth equations might look like, right? And it's a good to remember, sometimes leaving it as a natural log can be easier for our calculations, right? Because the natural log of 1.6 is a lot easier to plug into your calculator than the actual value, which is like 0.47000369292, right? That gets a little long and confusing, so sometimes it's just a lot easier to leave it in our natural log form. All right, so let's keep going. Let's look at number 4. At t equals 0, there's 50 grams of a radioactive isotope. The isotope has a half-life of 16 minutes. What is the rate of decay? Right, so it's asking for the rate, so we're going to be solving for r, and it gives us that the half-life is 16 minutes. So what we can do is we can say the amount after 16 minutes is going to be half of 50. So that would be 25 is the amount. The original amount is 50, right? And that's going to be times e raised to the rate, which we're solving for, times the time, which is 16 minutes. All right, we can do 50 divided over, right, which ends up being 0.5, and that's going to be equal to e to the 16r. We can convert that to our natural log form, right, which is ln of this 0.5 is equal to our exponent here, 16r. Right, we can solve for r, and r ends up being the ln of 0.5 all over 16. Right, and it's going to be roughly negative 0.0433, which if we convert that to a percentage, right, it's going to be negative 4.33%, right around there. So B is asking how many grams of the radioactive isotope are left after 20 minutes. All right, so now we're going to be solving for the amount. The original amount is still the same, it's 50 grams. Right, and that's going to be multiplied by E times our rate, which we just solved for. Right, and what we can do again, by plugging this in to our equation here, it's not going to give us an exact answer because we kind of rounded it out, right? We approximated. So it might be a little bit better to plug in our natural log form. Right, so the rate is just that ln of 0.5 all over 16. And that's going to be multiplied by the time, which is 20 minutes. Right, so this we can just plug into our calculator, right? we can do e raised to the ln of 0.5 divided by 16 times 20. We can multiply that by 50, and we end up getting that the amount is roughly, again, rounding it out here, 21.02 grams. Right? So number 5, a fossilized leaf contains 70% of its normal amount of carbon-14. How old is the fossil? Use 5,600 years as the half-life of carbon-14. Right? So what it's asking for is we want to know what's the rate that it's decomposing. Right? Because if we can find the rate, we can solve for the time it would take for it to go from 100% to 70%. Right, so we know it would take 5,600 years for half of it to decay. So we can kind of use that half-life equation where half of the original is going to be equal to the original times the e raised to the rate times the time, which is 5,600. Right, these p's are going to cancel, and we get 1/2 is equal to e to the r times 5,600. We can convert that to the natural log form, right? Because log base e, same thing as natural log of 1/2 is equal to r times 5,600. Right, and we can get the rate, again, in a natural log form, right? So we get rate is equal to the natural log of 1/2 all over 5,600. And right, to get an exact answer, we're going to leave it in this form so that when we plug it into our next equation, we get exactly the amount of time, right? So we don't have to round beforehand. So now what it's saying is that how long or how old is the fossil when it's 70% of its normal amount? All right, well, 70% of its normal amount would be 0.7 times the original amount. This is 70% of the normal amount. We can set that equal to the normal amount, which again, we don't know, but the cool thing is when we plug it in like this, right, we know these p's are going to cancel right away. That's going to be times e raised to the rate, which we have right here. It's the natural log of 1/2. Sorry, I know I'm writing kind of small here. All over 5,600. And that's going to be times the time which we're solving for, right? We want to know the time. So right away, these p's are going to cancel, and I'll try to write it a little neater this time. This is going to be 0.7 is equal to e to the ln of 1/2 all over 5,600 times time. Right? From here, just like we did in the other problem, we have to convert it to a natural log. So we get the natural log of 0.7 is equal to our exponent, which is the natural log of 1/2 over 5,600 times t. All right, so we can divide this whole thing over. Right? And remember, when we divide by a fraction, we're really just kind of flipping it to the other side. So we can say t is equal to 5,600 divided by natural log of 1/2. And that's going to be times the natural log of 0.7. Right? Which, not too bad to solve, right? We just do 5,600 divided by the natural log of 1/2 times the natural log of 0.7, and you end up getting that t is just about 2,881.61 years. All right, so last one. At time t equals 0, you have 100 grams of radioactive chromium-48. 10 hours later, you have 74 grams left. What is the rate of decay? All right, so we have the original amount, we have the new amount, and we have the time. So we just have to plug those into our equation to solve for R, the rate. So we can say the amount is 74. That's equal to the original 100 times E raised to the R, which we're solving for, and the time is 10 hours. All right, so we do 74 divided by this 100, and we get 0.74 is equal to E to the R times 10. And we convert it to our natural log, just like we've been doing. All right, so all of these problems are really similar. Right? A lot of the times we're going to be converting to that natural log. All right, so this becomes natural log of 0.74 is equal to our exponent, which we can rewrite as 10R. And so the R would be equal to, we can divide this 10 over, the natural log of 0.74 all over 10. Right? And we want to keep this because this is what gives us our exact answer, right? This is what we would plug into the second equation we're going to use so we can get an exact answer. But if we wanted to round it out a little bit, right, we can say that the rate is negative 0.03011, which if we wanted to write that as a percentage, it would be negative 3.011%. Right? Then B is asking, what is the half-life of chromium-48? Well, we know it's starting with 100, so we want to know how long is it going to take for it to get to 50. So we go 50 equals 100 times E raised to our exact answer here, the natural log of 0.74 divided by 10, and that's multiplied by the time which we're solving for. All right, we want to know what is the half-life. How long does it take for it to go from 100 to 50? All right, we can divide this 100 over, and we end up getting 0.5 is equal to E to that natural log of 0.74 all over 10 times T. And again, we're converting it to our natural log equation, right? Which would be the natural log of 0.5 is equal to our exponent here, which is that natural log of 0.74 all over 10. That's equal to T. So this is really similar to what we just did in the problem before, number 5, right? Because we're going to divide this over, which ends up just flipping it to the other side. So we end up getting T is equal to that 10 over natural log of 0.74. And that's all going to be times the natural log of 0.5. Which when we solve that, we end up getting that the time is equal to 23.02 hours. All right, thanks for hanging out, guys. If you have questions, just let us know.